In this video, we'll introduce several matrix algebra concepts that are going to come in handy. After studying this video, you should be able to identify several special matrices that often arise in numerical methods. Also, you should be able to perform matrix multiplication and knowing how it works so you can do it by hand. You should be able to define some basic matrix algebra concepts such as the determinant, matrix inverse, and a matrix norm. Write a linear system of equations in matrix form. And the reason we do that is it gives us a more compact form for analysis. Also, I want to note that we're going to leave the majority of the theory and proofs underlying these ideas to your linear algebra course, Math 260 for most of you. We're just going to introduce enough theory so that we can focus on applying some numerical methods to linear systems. So let's start with some basic matrix concepts. We'll refer to a matrix A as any table of numbers, basically. And the table consists of rows and columns. And we can talk about any individual element in the matrix with its row column index. And oftentimes we'll refer to that as A, I, J. Lastly, we'll look at the overall matrix size as having M rows by N columns. So the lower right corner of the matrix would be AMN. Once we have a matrix, one basic concept we can introduce is the transpose of a matrix. The transpose of a matrix is when the rows and columns are switched. So here's a simple example with a 2 by 2 matrix. We see the diagonal elements stay the same. They stay the same, and we've just basically switched the 3 and the 2 in the transpose. Transpose operator in MATLAB is an apostrophe. Here are some special matrices that identifying these can often help in implementing efficient numerical methods. If we have a symmetric matrix, we can see the elements are the same on either side of the diagonal. So we have a 1 and a 1, 2, 2, and 7, 7. You can see how that is symmetric across the diagonal is what we mean when we talk about symmetric. A diagonal matrix includes only elements on the diagonal, and the rest is all zeros off the diagonal. The identity matrix is a matrix that just has a diagonal of all ones and zeros everywhere else. We can also have an upper triangular matrix, which consists of all zeros below the diagonal, and a lower triangular matrix, which consists of all zeros above the diagonal. Lastly, we can talk about banded matrices, and that's where we have a diagonal plus one or more bands on either side of the diagonal. In this example, this would be a tri-diagonal matrix. Matrix multiplication has a special definition. This is the default in MATLAB and why we have been needing the period before the multiplication operator to do something different. The elements in a matrix C that results in multiplying matrices A and B are calculated as follows. And here is a calculation in summation notation, but I think it's easiest just to walk through an example. So if C is equal to A times B, then C is equal to, what we do is we go across the rows and down the columns. So it would be -1 times 1 plus 2 times 4, and that would be in the first row, first column, and then -1 times 3 plus 2 times 2. That would be in the second column, first row. Then we can move down to the second row and we get 1 times 1 plus 2 times 4 and 1 times 3 plus 2 times 2. And lastly, we get 3 times 1 plus 1 times 4. And for our last element, it's going to be again 3 times 3 plus 1 times 2. And we see that the final matrix has the same number of rows as A and the same number of columns as B. In this case, we have 3 rows and 2 columns. This is a 3 by 2 matrix. Another thing that's important is that the interior dimensions of the matrices, so the number of columns in A must be equal to the number of rows in B. And notice this matrix wouldn't be possible. B times A is not possible, which tells us that this is not a commutative operation. So let's talk about some more matrix concepts. Here's a matrix determinant, something you may have encountered in statics or in other algebra classes. The determinant of the matrix A, and note the straight lines, not a square bracket, to define that determinant, is defined as follows. We can go through and take A1 times the determinant here minus A12 times this determinant that uses those two and these two minus A13 times this determinant. And we see that here. Here is the first blue determinant times A12, the second red determinant, and the third green determinant. And each of those determinants are calculated as follows. We do A22, the upper left times the lower right, A22 times A33 in this case, minus the upper right times the lower left. So that would be the definition of each of these determinants. Note that the result is a scalar, not a matrix. This is going to equal some number. And also note that the determinants of larger matrices can be determined in a similar fashion. So for example, a 4 by 4, we would then go to a linear combination of 4 3 by 3 determinants, and that would go, each of those 3 by 3 determinants would give us 3 2 by 2 determinants, so we'd have 12 2 by 2 determinants, and then we'd have our result. As you can see, for a larger matrix that can quickly become very tedious, luckily MATLAB has a built-in function to calculate determinants. It's a fairly straightforward arithmetic algorithm, and it's in the function det. Matrix inverse is another key concept. The inverse of a matrix is defined such that A times its inverse, the minus 1 indicates the inverse, is equal to A inverse times A. So in this special case, we are commutative only when we're multiplying a matrix by its inverse, and the result is the identity matrix. And recall that that identity matrix again is 1s on the diagonal and 0s everywhere else. And we're not quite ready to do this calculation by hand, but it's important that we know this definition. It should, because this is commutative, it should be apparent that it needs to be a square matrix in order to have an inverse. A couple other notes. A matrix is said to be singular if the inverse does not exist. That's the definition of a singular matrix. That inverse does not exist. Another note is that the determinant of a singular matrix will be 0. So that's one helpful thing that the determinant can tell us is whether a matrix is singular. MATLAB does have a built-in function to calculate the inverse A, or we can just raise A to the -1 power. Either one will calculate that inverse. We'll talk about how you can calculate an inverse by hand in a later video, and you'll definitely cover that in your linear algebra course. The next concept I want to introduce is the idea of a norm. A matrix and a vectors both have norms. Norms provide a scalar that gives an indication of the magnitude of a vector or matrix. For scalar numbers, we can look at their absolute value and get a sense of their magnitude, but sometimes this is hard to tell from a matrix. And a determinant is not necessarily the best measure since it includes those subtractions, as we saw. There's lots of examples of norms that are useful for different purposes. I've provided a few examples here. The double lines indicate a norm in terms of notation. So the Euclidean norm is something you should be familiar with if you thought of, say, the magnitude of a Cartesian vector. You've covered vectors, Cartesian vectors in, say, statics or physics. Again, this is the square root of the sum of the squares of the individual elements. We can expand that idea for a matrix, which is just the square root of the sum of the squares for all elements. So we take all of the elements of the matrix, square each one, sum them up, and take the square root. And that gives us the Euclidean norm for a matrix. So another example of a norm is a column sum norm. And for this column sum norm, what we do is we go through all of the columns. For each column, we sum the absolute value of all of the elements and then take the maximum result. So whichever column has the maximum sum of its absolute values. And we'll talk about how we use these norms in a later video, but they can tell us something about how that matrix will behave. And as I said earlier, a more comprehensive treatment of this concept is beyond our scope, but we do want to be familiar with the basic idea of a norm as a way to give a single scalar value that indicates the magnitude of a matrix. Matrix notation provides a compact way to represent linear systems of equations. So we can look here. Here's a 3x3 system. And we can see how by applying the definition of matrix multiplication, this is a 3x3 system of equations. So again, going across the row and down the column, we have A11 times x1 plus A12 times x2 plus A13 times x3 equals B1. A21 times x1 plus A22 times x2 plus A23 times x3 equals B2, and A31 times x1 plus A32 times x2 plus A33 times x3 equals B3. So in general, the first thing that you want to do to write a linear system in matrix notation, we're usually starting from this point and just organize the equations such that the coefficients for each variable are lined up as they are here. There's the x1 coefficients, the x2 coefficients, and the x3 coefficients. And then you can just take those coefficients and put them into the coefficient matrix, which we'll generally call A, and move all of the constants over to the right-hand side, and that gives us our right-hand side vector, or B. And then we can write this in compact matrix notation by saying the matrix A multiplied by the vector, and again that's a column vector, x, is equal to the column vector B. And in that notation, note a capital A, capital bold means matrix, and the lowercase bold font would be a vector. And we can gain a lot of understanding about how the linear system will behave numerically by looking at the properties of that matrix A, that coefficient matrix. And we'll talk more about that going forward. So solving a linear system in MATLAB is actually pretty easy. There's three basic approaches. We've defined a linear system as AX equals B, meaning we've inputted matrices or vectors for each of those three variables. We can take the following three approaches. One is matrix left division. Simply use the backslash operator, and MATLAB will return the solution vector x. Or we can use the matrix inverse in either way. Note, if we have AX equals B, we can simply multiply both sides by the inverse, or IX equals A minus 1B, but since that's the identity matrix, that's just X is equal to the inverse of A times B. So we can use that to solve for the inverse. MATLAB can also return what's called reduced row echelon form using the ref function, and I'm going to leave that to your linear algebra. It's common in linear algebra, but one of the reasons that we won't use this in Engineering 240 is because the output is not a simple vector of x values. So one thing to note here is that the left division operator is the preferred approach. It's more computationally efficient, and in fact it can handle overdetermined systems. And we'll talk more about why in the coming videos, but we need to cover a little more background first. There's actually a lot going on with just that simple left division operator. We could definitely say it's more than meets the eye. And again, the following videos are basically going to build up how that works.